Okay. I want to make just a quick comment about memory organization, and this is in context of the program where we printed Y's address, Y pointer's value, and then Y pointer's address. So I executed that program on a machine that was 64 bits, but it also had a 64-bit address space. And each byte is 2 hexadecimal characters. So memory in a computer is organized like a table, and the first entry of the table is at 0. And this is what the lowest address looks like in a computer with 64 bits, right? So we have 8 bytes that we're using to represent, and each of these, here's 1, 2, 3, 4, 5, 6, 7, 8. And you know that hexadecimal digits go to F, so the largest location is one that has all F's. And this is just one big table. This is the address, and then we can store information. We can store information at these addresses. So, for example, we could put, integers and characters and things like that over in these address spaces. Really, everything is binary. It's a matter of interpretation, what makes something a character versus a double, but we'll ignore that for right now. Now, we're not going to talk about how a computer operating system chops this memory up, but there are certain areas that are reserved for the operating system, and then there are certain areas of memory that are reserved for use for user programs. So when we ran our user program, it put Y at 7FFF 319707B8. And we just had a padding of zeros over here that it didn't print. And so somewhere in here, this is where our program was running, and this is where it put Y's address, and then it put Y pointer's address at B0. I'm not going to copy this whole thing, but out here at 07B0. So this was where Y pointer was, and this is where Y was. And notice that, we declared Y first, it went here, and then Y pointer, we declared it second, and it actually went above. So the program as it's running is actually filling memory up like this. And also notice that we have 0 here and 8 here, and so that suggests that there are 8 memory locations between here and 8. So 1, 2, 3, 4, 5, 6, 7, and 8. So there are 8 bytes that we're using to store Y pointer. And if we would also be able to figure out the extent of Y. So, each of these address locations doesn't correspond to a single object. Depends on the size of the object. So large objects are going to require more of these address locations to store. Well, it turns out that if you use the size of function to get the size of a pointer to a double, you'll see that it's 8 bytes, and that's why Y pointer starts here, and we know that this pointer is 8 bytes, and so we can calculate the range over which the computer has stored Y pointer. So this is just an example of how. And in this address, what we would do is the components of this address would actually be stored at these locations, and that's how we get this pointer. So if each location can store 2 of these bytes, that's how we get 8, then 0, 0 will be stored here, 0, 0 will be stored here, 7F will be stored here, FF, 3197 and 07 and B8. And that's how in Y pointer we're storing this address that tells us. Now, Y's value, whatever the binary representation of 5.3, is going to be stored in this area here. So this is going to be the binary representation of 5.3. And you'll learn more about this in your hardware and systems class, but I just wanted to explain a little bit of what these addresses mean and what's actually being stored.